So in problem 27 in section 1.9, we want to determine if the transformation is one-to-one and onto. So here's the transformation from problem 19. T of x1, x2, x3 is x1 minus 5x2 plus 4x3, and then x2 minus 6x3. So the transformation goes from R3 to R2, and we want to find the standard matrix of the transformation. So we get there by mapping the basis vectors. The image of 1, 0, 0 will be 1, 0. The image of 0, 1, 0 will be negative 5, 1. And the image of 0, 0, 1 will be 4, negative 6. We can also get at the standard matrix of the transformation by looking at these entries and then just writing them as rows. But that's a mechanical way of doing it. That's not us thinking about how the transformation works. So we want to think about how the transformation works. Now 27 specifically asks if the transformation is one-to-one and onto. To get there, we need to know where the pivots are in the standard matrix of the transformation. Where are the pivots in the standard matrix of A? What's the reduced row echelon form of A? I'll do the first column. The first column is 1, 0. What's the second column of the reduced row echelon form? So we definitely have a pivot here. Got a pivot in that first row. What's the second column of the reduced row echelon form of the standard matrix of the transformation T? Anyone have it yet? 0, 1. We can tell that either because we're going to use our calculator, or we can say, hey, this second column is not a multiple of the first column, so there's going to be a pivot there. Then the third column is not going to be a pivot column because we out of pivots. So there'll be some third column. Actually, we can easily find that. So we got 5 times the second row plus the first row. So 5 minus 5 is 0. And then negative 30 and 4 is some number. Negative 30 plus 4 is negative 26. It doesn't matter because we knew we were not going to get a pivot in the third column because we out of pivots. So since A is the standard matrix of T, there are two questions. We want to know if the transformation is one-to-one and onto. One-to-one means that if T of x is equal to T of y, then x equals y. That means that T of x equals, that means the columns of the standard matrix are linearly independent. That means the standard matrix has a pivot in every column. That's not the case here. So we would say T is not one-to-one since the standard matrix of T does not have a pivot in each column. A pivot in each column, unique solutions, that's what goes with one-to-one. Notice that we're using the matrix and the pivots in the matrix to determine something about the transformation. Notice that T does not have a pivot in each column. It's not that T does not have a pivot in each column because T is not a matrix. The matrix of T does not have a pivot in each column. A thing about transformations for a transformation, a thing about matrices for a matrix. We can conclude that T maps R3 onto R2 because the matrix of T has a pivot in each row. T maps R3 onto R2 since the matrix of T has a pivot in each row. Any questions? Go through pivots anytime you can, but remember, it's a matrix that has pivots. A matrix has pivots. Transformations are one-to-one or onto. We ran out of pivots because we only have 2 rows. With only 2 rows, we can only have at most 2 pivots. It's not about R2 or R3. We ran out of pivots in the 2 rows. If the matrix meant from R2 to R3, and if the transformation ran from R2 to R3, then the matrix would be 3 by 2, and we could have at most 2 pivots, but this time because of the columns, not the rows. Yeah, we just don't worry about the number of pivots. Are all the rows filled with pivots? Are all the columns filled with pivots? That's how we make our decision. More importantly than writing this sentence and making sure that we have a matrix of the transformation with the pivots, and then the transformation is onto, we have to make sure the words are going together there. Look at all the other things that we get. So pivot in every row means the columns of the matrix span all of R2. And that's what it means to say that T maps R3 onto R2. That means that T of X T of X equals B is consistent for all B in R2. So pivot in every row means some equation is always consistent. So this statement is equivalent to saying that T of X equals B is consistent for all B in R2. Because the matrix of T has a pivot in every row. And that's what we get for a pivot in each row. And that's why we call it onto R2. It takes 3 and completely covers onto. The range of T is equal to the codomain of T. The range of T is equal to the codomain of T. The T takes all the vectors from R3 and completely covers R2. The range of T is equal to the codomain. Everything in the codomain is an image of something from the domain. When we think about it that way, we realize that this transformation could not possibly be one-to-one, because one-to-one is associated with unique solutions. And if we take a 3-dimensional thing and use it to cover a 2-dimensional thing, then we got a whole extra dimension left over. In particular, we got 1 extra dimension. And here's that 1 extra dimension. It's like all this stuff is supposed to be connected or something. So we knew we're going to have some free variables. This is going to have to map a bunch of things to 0 if we're going from 3 dimensions all the way down to 2 dimensions. There's going to be a bunch of stuff that has to get mapped to 0. Any questions? Cool. Perfect question. I don't know if I asked 19 separately from 27, but if I only asked for 27 and it referred to problem 19, so you kind of had to do problem 19 to do 27, that's kind of like a 2-for-1 deal. So sometimes I do that. All right, let's pause this video and talk about where we're headed next.